If we have a collection of many points, like we earlier discussed with momentum, points that interact with each other. It could be stars who gravitationally interact. It could be objects which are connected with springs. They have internal interactions which go on all the time. They bounce off each other. They collide. They break up in pieces. Internal friction, anything. Then, if I take two of these objects, if this one, for instance, is attracted towards this one, then action equals minus reaction, then these two forces are identical in magnitude. So if I take any point Q here, no matter where you choose it, that will never put a torque on that system, because the two forces cancel each other out. And so now we get the final conservation of angular momentum. It's all its glory if only we add here one little word, external. The angular momentum of a system, this was angular momentum of just one object. This is the angular momentum of a system of many particles. They could be connected with springs. There could be chemical explosions going on. They could plow into each other. They could break each other up. The angular momentum will not change if there is no net external torque on that system, because all the internal torques cancel out, because action equals minus reaction. So if we now compare conservation of angular momentum with conservation of momentum, then in the case of the conservation of momentum, remember when we had a system of objects, in the absence of an external force on the system as a whole, a net external force, momentum was conserved. Now we have, with a system of particles, in the absence of a net external torque, angular momentum is conserved. In the case of the ice skater's delight, when you pull your arms in, the moment of inertia goes down, and so your frequency goes up. When a star shrinks, its radius goes down, its moment of inertia goes down, and therefore its angular velocity must go up. Moment of inertia goes with r squared. What determines the size of a star? If this is a star, then inside this star is a furnace, a nuclear furnace. Nuclear fusion is going on. That produces heat and pressure, which wants to expand the star. On the other hand, there is gravity, which says, sorry, you can't do that. I want to hold you together. In fact, gravity would like to collapse the star. And nature finds a balance between the gravity and this pressure due to the nuclear furnace. Now there comes a time that the nuclear furnace has been completely consumed. For our sun, that takes an additional 5 billion years. The sun has already been burning nuclear fuel for 5 billion years. It has another 5 billion to go. And once the nuclear fuel has been consumed, there are 3 end products of the dead star that is left over. And these 3 end products are the following. Number 1, it's called a white dwarf. It has a radius approximately the same as the Earth, some 10,000 kilometers. And the mass of a white dwarf, there's a whole range of them. But a typical number, say, is half the mass of the sun. So that's one possible end product. This will be the fate of our sun, by the way. The density of such an object is quite high. Some 10 to the rho will be roughly 10 to the 6 grams per cubic centimeter. Another possibility is that you end up with a neutron star. A neutron star has a radius of about 10 kilometers, and it has a mass of roughly 1.5 times the mass of the sun, and its density is about 10 to the 14 grams per cubic centimeter, which is even higher than the density of nuclei. And then there is a possibility, which is even more bizarre, that you end up with a black hole. I will not talk about black holes today, but I will get back to that later in 801 And a black hole, for all practical purposes, has no size at all. The mass of the black hole must be larger than, we think, 3 solar masses, and so the density is infinitely high. Whether you end up to be a white dwarf, a neutron star, or a black hole depends on the mass of the progenitor, of the star that collapsed when the nuclear fuel was gone. And in order to form a neutron star, you would have to start off with a star of probably at least 10 solar masses, maybe even more. So our sun will not become a neutron star, but our sun will ultimately become a white dwarf. Now, it would be a reasonable question to ask, why do you end up only with these 3 possibilities? Why is there nothing in between? Look, there is a huge difference from 10,000 kilometers to 10 kilometers. Is there nothing in between? And the answer to that lies in quantum mechanics, which is not part of this course, but you will see that in 805, why there are only these 2. And then if you get into general relativity, then you will understand why there is then this 3rd, very bizarre possibility. When a star collapses, 2 things happen. First of all, there is a huge amount of gravitational potential energy that is released in the form of kinetic energy. The stuff falls in, we call it gravitational collapse, and that gravitational potential energy converts to kinetic energy, and that ultimately converts to heat and to radiation. If I take an object here, a piece of chalk, and I drop that you can call gravitational collapse. Gravitational potential energy is converted to kinetic energy, and ultimately it goes to heat. Here we're talking about a star which is imploding, collapsing, and the amounts of gravitational potential energy that become available are enormous. In addition to this huge amount of energy release, the star must spin up because its moment of inertia goes down, and therefore the angular velocity must go up. I want to do a little bit of quantitative work on this, and I want to take an object like our sun, and I would like to collapse that object from its present radius of the sun, which is about 700,000 kilometers. I want to collapse that to a neutron star with a radius of 10 kilometers, even though I know, and I told you, that the sun will not become a neutron star. It's just to get some feeling for the numbers. So we take an object like the sun, which has a radius of about 700,000 kilometers, and we're going to collapse that to a neutron star, which has a radius of about 10 kilometers. The mass of the sun is 2 times 10 to the 30 kilograms. And for those of you who are good at math, they can calculate when you collapse this object without losing any mass, you keep all the mass, but you shrink it to 10 kilometers, how much gravitational potential energy is released. And that is a staggering number. And I call that delta U. It is a loss of gravitational potential energy, which is about 10 to the 46 joules. And this number is truly mind-boggling. This is converted to kinetic energy, and then it is converted to heat and all forms of radiation. To give you a feeling for how absurdly large this number is, if you take the sun and you take all the energy that the sun produces in its 10 billion years that it will live, the total energy output of the sun is 100 times less than this number, and this comes out in a matter of seconds. So it is a mind-boggling idea that the sun is producing in 10 billion years, the lifetime of the sun, it is producing less energy than what happens during a stellar collapse to a neutron star. 100 times less. So when this infall occurs and this huge amount of energy is released, the outer layer bounces off the inner core and is expelled, and that's what we call a supernova explosion. The outer layers are thrown off with speeds typically some 10,000 kilometers per second. Our sun will not become a neutron star, but it will become a white dwarf. We talked about the Crab Nebula last time, and the Crab Nebula is a remnant of a supernova explosion which occurred, believe it or not, on the 4th of July in the year 1054, talking about fireworks. This supernova explosion was noticed by Chinese astronomers. They called this a guest star. Chinese astronomers were very prestigious. The reason for that was that these Chinese astronomers advised the emperor. They looked at the sky and they derived from the sky information that was key for the emperor. They knew how to interpret the occurrence of comets, or for instance, shooting stars, or a particular lineup of planets, and certainly the appearance of a guest star. And they would know that, for instance, a comet in a certain part of the sky might mean that there would be hunger, or there would be diseases, there would be famine, or it would be a good time for a battle, or it would be a bad time for a battle. And that's what these people were doing. They were advising the emperor, and therefore they were keeping a very close eye on the sky, no pun implied. This star was visible for weeks during the day when it exploded, and it was the brightest star in the sky for years to come. It is a complete puzzle why there isn't a single report by any European astronomer on the occurrence of the supernova of 1054. It is very puzzling. Now you can argue that in the Netherlands and in England there are always clouds, it's always raining, so you can't see the sky. Okay, I grant you that. But then we have Italy, and we have Spain, and we have France. And it is very strange. It must have been a cultural thing somehow. In the 11th century, somehow, Europe was not interested in looking at the sky. This is something they could not have missed. But they didn't write it down. I now want to pursue the spin-up of this star when it collapses from 700,000 kilometers to 10 kilometers. If we round the numbers off a little bit, then the reduction in radius is about 100,000. It's really only 70,000, but let's just make that 100,000, 10 to the fifth. That means r squared goes down by a factor 10 billion. And if r squared goes down by a factor 10 billion, then the moment of inertia goes down by a factor of 10 billion. And so omega must go up by a factor of 10 billion. If you started off with a star that rotated about its own axis in 100 days, it ends up rotating around in 1 millisecond when it has become a neutron star. A neutron star, 10 kilometers. It has about the same mass of the sun, a little more. And it spins around in 1 millisecond. At the equator of the neutron star, you reach about 20% of the speed of light. We know of hundreds of neutron stars in the sky. 2 of them have, in fact, rotational periods of 1.5 milliseconds. Many of them much slower, and we discussed last time why that is. Because remember, in the case of the Crab pulsar, the pulsars slow down. Nature is tapping on the rotational kinetic energy of these pulsars and is converting it into other forms of energy. In the case of the Crab pulsar, radio emission, optical emission, gamma rays, X-rays, and even jets. The Crab pulsar was slowing down every day 36.4 nanoseconds, which led to a staggering power output. I still remember the number, I think 6 times 10 to the 31 watts. In 75 years, the pulsar slows down by 1 millisecond. So the 33 milliseconds would become 34 milliseconds in 75 years. If the star has an original, there's no star, it was a disk, right? If the star has an original magnetic field, which most stars do, oh, I lost my star, but that's okay. Then in the collapse, the magnetic field will become stronger. And this is something you will learn about in 802, why it becomes stronger. So most of these neutron stars have strong magnetic fields, and most rotate very fast. And for reasons that we don't quite understand, many of them blink at us. They blink at us in radio emission. We believe that there are 2 beams of radio emission, like a lighthouse, going out from the 2 magnetic poles of the neutron star. And as the neutron star rotates, and you are on Earth, if it sweeps over you, you see radio emission, you see nothing, you see radio emission, you see radio emission. So many pulsars whose beam doesn't sweep over the Earth, we would never be able to see, of course. And in the case of the pulsar and the crab, it's even more special because that pulsar also blinks at us in the optical, in the X-rays, and in the gamma rays.